So yeah, good evening. You are able to hear me, right? Okay. So today is the week 11 of the live interactive session for the NPTEL course, an introduction to climate dynamics, variability and monitoring. Uh, yeah. So today we will start with solving the assignments from I think week 8, I guess, where you learned about ocean, different ocean properties, the El Nino Southern Oscillation, Walker Circulation, etc. So the first question was regarding the properties of thermocline. So the question is the temperature at the bottom of the permanent thermocline is stated to be between 4 to 5 degrees Celsius at low and mid latitudes. What is the temperature of the bottom of the thermocline at the poles? So just sorry, 0 degrees Celsius. Yeah. So just to remind like what thermocline is and all those things. So basically the temperature of the ocean ranges from minus 2 degrees Celsius to 30 degrees Celsius. And the average temperature of the ocean is around 3.6 degrees Celsius. And basically the ocean is divided into three regions, which is the topmost layer, which is known as a mid layer. This is the first layer in the ocean, which is basically stirred up by the winds and the waves. So it basically have temperature and salinity values almost uniform with respect to depth. And below the mid layer, we have the thermocline. So thermocline is where there is a rapid, it is basically a region of rapid change in temperature with respect to depth. Rapid temperature change with respect to depth. So yeah, so thermocline is a region where there is a rapid temperature change with respect to depth. It generally lies below the well-mixed layer and it extends up to a depth of 1,000 meters below the sea level. And the temperature at the bottom of the thermocline is 4 to 5 degrees Celsius at low and mid latitude. So if you look at here in this figure, this region, so this is during different season. So this is basically during summer, I guess. Sorry, this is during winter. So we can see that. So if you look at the red line, the Valmet's layer or the layer where the temperature and salinity values are almost constant with respect to depth is the mixed layer. Then below that we have this thermocline where there is a large temperature difference with respect to depth. And below that we have the deep layer where the temperature and salinity values are uniform. The third one is the deep layer where the temperature and salinity values are uniform with respect to depth. It slowly drops from 4 degrees Celsius at the base of the thermocline to 2 degrees Celsius at the ocean bottom. And if we are looking at the polar regions, it may drop up to 0 degrees Celsius as well. So, in case of the permanent thermocline, the temperature at the bottom, that is below before the deep layer starts, the temperature at the bottom of the thermocline is around 4 to 5 degrees Celsius over the poles. So, around 4 to 5 degrees Celsius at low and mid latitudes or like in the equator. So, this red line basically shows in case of the equator. Here we can see, this is the thermocline region where we are able to see a rapid decrease in temperature with respect to depth. At around 500 meter, we can see the temperature is coming down around 500 to 800 meter. We are able to see a temperature of 4 to 5 degrees Celsius. Whereas in case of the polar regions, such as the dotted blue line, 75-degree north to 75-degree north, basically, this one we can see around this level before this temperature and salinity values become uniform, the temperature drops to approximately 0 degree Celsius. So the permanent thermocline over the lower latitudes, the temperature bottom of the thermocline has a temperature of 4 to 5 degrees Celsius, whereas over the polar regions, the bottom of the permanent thermocline has a value of around 0 degrees Celsius. And as along with this variation with respect to latitude, the thermocline also shows difference with respect to seasons as well. As we can see, this one, the first one is for February, and the second one is for winter or August. Sorry, the first one is for winter, and the second one is for summer. And yeah, okay, yeah, yeah, over the equator, right? It could be due to precipitation also. If like large precipitation is there, it may reduce the temperature. So 25-degree west is it could be due to that also, like proper yeah, proper matching. Yeah, winter should be low. Okay, winter it is higher and summer it is lower. Okay, during winter it is high, 25. Okay, let me just check actually. Yeah, I like yeah, over 0 degree. It is during February. What is the sun will be over which region? Like it will be sun will be in the northern hemisphere, no? Will be in the northern hemisphere. So I think February, January, February time sun is mostly directly what you say. Yeah, it is directly over the northern hemisphere. So that could be the reason we are having higher temperature. In January, the sun is directly overhead the Tropic of Capricorn. That is like 23.5 degrees south. So that's why during December, January, February, we have this winter time. So December, January, February is considered as northern hemispheric winter. And during July, we have it over the 20 over 23.5 degree north, I guess. Like, yeah, July we have it over. Yeah. So during January, it is over the southern region, but still we have very high temperatures. That is the issue, right? In the surface. That could be another reason could be due to like lower wind speed. If mixing is less, then we will have like stratified ocean layers. If we have very less wind speed over the oceans, or like, yeah, so then this mixing won't happen. So whatever is the temperature is over the surface, it will remain. If the surface layer is very shallow, we will have very high temperatures near the surface. And when we have higher wind speeds or higher winds over the ocean, then well mixing will happen. Then the stratification will go. So we will have a deeper mixed layer and a lower temperature as well. So that could be the reason because of, yeah. So during February, I think methane is less. So we have, so you can see also the methane layer is very shallow. Like this region is very shallow. So maybe that's why we have that stratified layer. Whereas during January, we have a little bit deeper methane layer. I think that is the reason. Is there any other possibility? Yeah. So I think it could be due to that. Whatever this figure shows, I think it could be because of that. So February we have a temperature of around 26, 27, and here we have 26. Okay, over the equator. And then 25-degree north we have around 20, 22 in 25-degree north, and here it is again 25. I think, and also like the winters and summers are not that what you say distinct in, like it will be mostly moderate. Winters won't be that strong in the equatorial region, I guess, because it anyway receives like some amount of solar radiation. It could be because of that also you are not able to see that much difference. But like over high latitudes, I think that distinction is clear. Like summers are actually having higher temperature and winters are having lower temperature. So it could be due to the latitude also. Equator, we are not clearly able to see that. But as we go in higher latitudes, that distinction is clear in the surface layer. So it could be because of that also. Yeah. Yeah. So the answer to the question is 0 degrees Celsius. And as I said, thermocline shows difference with seasons as well as with latitudes. Over high latitudes, mudslide layer is, so yeah, if you can see, the mudslide layer is very shallow during summer. Like here, this blue dotted line at 75-degree north and 45-degree north, you can see the mudslide layer is very shallow during summer, whereas the mudslide layer is deep during winter. And during over the equator, the mudslide layer temperatures are high, and we have a very steep thermocline. So if you look at the temperature difference in the thermocline, we can see that it is very deep compared to the other latitudes. So yeah, so that is the basic idea of thermocline. How what are the basic different layers in the ocean, etc. Now the next question. Seawater is slightly compressible, and this compressibility effect by itself does not change the density and temperature of seawater with depth. Compressible in the sense like its density changes, it shows, or it is possible for it to have a change in density. So it is said that the seawater is slightly compressible, which means its density changes, and this compressibility effect by itself does not change the density and temperature of seawater with depth. So it's like true or false question. Since the seawater is compressible, does it change the density and temperature of seawater with depth? It does not change is what is given in the question. So what do you think? Will it change or will it not? It is false, yeah. So at for high pressures which are found in deep oceans, over deep oceans at very high pressures, the seawater is compressible, or like it becomes compressible at over the deep oceans at during high pressures. So it does change with depth. At high deep oceans only we are able to see that the seawater is actually compressible. And this compressibility effect will change the density and temperature of seawater with respect to depth. So generally, in order to remove, since at different depths we have, since the seawater is compressible, instead of using the actual temperature and salinity, so it matters at what level we are actually considering the seawater. So when we look at the temperature and density profiles, what we do is that we consider what is known as, instead of using the actual temperature and density, the potential temperature and potential density is used in order to account for the variation of the density of the seawater with respect to depth. So this we have used in the atmosphere also. So I think you know what does it mean by potential temperature or potential density. Same definition as that of in the atmosphere. So it is basically the value that a parcel of seawater will have, a parcel of seawater at a particular depth will have, if that parcel is adiabatically brought down to a chosen reference pressure from its original pressure. So it's the same definition as that of the in case of atmosphere also. So in order to account for the change of the density of seawater with respect to depth, we generally use potential temperature and potential density while doing calculations or while looking at the profiles. So the answer to the question is false. Now the next question. The Atlantic Ocean is markedly saltier compared to that of the Pacific Ocean, primarily because it receives less rainfall and has higher evaporation. So, what is the condition for high salinity in terms of evaporation and precipitation? Highly saline means which one will be higher? Yeah, that I understand. Yeah, that is fine. So, if you look at the, so we are telling that a particular ocean is highly saline. So, what does it say about the evaporation and precipitation rate at that ocean? Which one will be higher, evaporation or precipitation? What if a region receives very high precipitation? It will be high saline or low saline? Yeah, precipitation means low saline. So, highly saline in the sense evaporation will be less than the precipitation. No, highly saline means evaporation will be high. Yeah, evaporation will be greater than precipitation. High evaporation will be there, so evaporation will be greater than precipitation. Whereas low saline means evaporation will be less than precipitation, or precipitation will be more. So the first question was the first option is it receives less rainfall and has higher evaporation. So yeah, that is a possibility for it to be highly saline. And the second one, it is surrounded by continents with large amount of salt runoff and loses more water through evaporation than it gains via rainfall. Yeah, the second one is the correct. So when you compare the Atlantic Ocean and the Pacific Ocean, you can see the Atlantic Ocean is mostly surrounded by the continents. So due to the salt runoff from the land, the Atlantic Ocean is found to be more saltier compared to that of the Pacific Ocean. So yeah, the second one is the correct answer. So it is surrounded by continents with large amount of salt runoff, and it also loses more water through evaporation. That is, evaporation is greater than precipitation. So that's why the Atlantic Ocean is more saltier than the Pacific Ocean. Yeah. Now the fourth question: the average depth of the method layer in the ocean is about. Mm, yeah. So the average Metzeler depth, that is like the region where we are able to see almost constant temperature and salinity from the surface. So it varies with respect to latitude and varies with respect to seasons. On an average, it is approximately having a value of 70 meters. From this itself, we can see that it is very shallow, like it is very close to the surface only. We will be able to see that Metzer layer. Now the next question. The net effect of Ekman transport. is that the water is transported at a direction of 45 degree to the right of the wind direction in the northern hemisphere. Is it true or false? Yes. Yes. So what is mean by Ekman transport? I will just explain once. Let me add one additional slide so that I can. So what does it mean by Ekman transport? So the transfer of momentum from winds to ocean currents. Suppose we have ocean and like wind is so this is ocean surface and there is a wind that is blowing from west to east on top of the ocean. So because of this wind, the wind will take the surface water along with it, and the surface water will also experience a momentum along with that of the wind. So basically, the transfer of momentum from winds to ocean currents basically play a critical role in driving the ocean circulation systems. So the uppermost layer of the ocean are dragged by wind-driven frictional acceleration. So this wind will drag the surface that is below it. This surface will drag the surface below it, and it will drag the surface below it. It is kind of like that. The momentum is getting transferred to deeper and deeper layers. So the depth over which the wind-driven surface current is generated is called the Ekman layer. So up to which the effect of this wind will be there, that layer is basically known as the Ekman layer. And this actually happens up to the base of the well mixed layer. So this when driven currents are basically seen in the mixed layer or up to the base of the mixed layer is generally known as the Ekman layer. So we have a wind that is blowing along the surface of the ocean. So the wind, as it moves, it drags the surface as well along with it. So the surface layer again imparts a momentum to the layer below it, that layer below it like that. So it is getting transported with respect to the depth, with respect to depth. And this the depth over which this wind-driven surface current has an effect or it generates surface currents are basically known as the Ekman layer. Now consider we have a westerly wind. So it is blowing westerly in the sense which direction it will be coming. If we have a westerly wind, it means the wind is blowing from which to which direction? Yeah. So we have westerly. So it is west to east, a wind is blowing. So as we said, this will drag the surface water along with it. So as the surface current starts to move, because of the rotation of the earth, the Coriolis force comes into play. And you know that the Coriolis force is basically defined as F into Vi minus Uj, where F, which is the Coriolis parameter, is given by F is equal to 2 omega sine phi, where omega is the speed of rotation of the Earth, which is 7.29 into 10 raised to minus 5, right? Minus 5 or minus 4? 7.29 into 10 raised to minus 5, I guess. And phi is the latitude that we are considering. 10 raised to minus 5 or minus 4? Rotation, not meter per second, it is radian per second. 7.27 into 10 raised to minus 5 radian per second. Yeah. So this is F Coriolis. So as the surface current starts to move, the F Coriolis will begin to act on it. So as we said, the motion is actually from west to east. So which one will be here, V or U? Which one will be 0 if the motion is west to east? West to east in the sense it is the motion is zonal or meridional. Yeah, F Coriolis is MF into VI minus UJ. Since the motion is from west to east, it is a zonal motion. So the meridional component, which is V, meridional velocity V will be 0. So our force F Coriolis reduces to minus M F U J. Okay. And this is acting in which direction? If you're yeah. Minus FU. So it is basically in the north-south direction. Sorry. It's minus 4. Is it? Let me check again. 10 raised to minus 5 is correct, I guess. No? Is it? Okay, I'll check that. Anyway, I'll check that. We'll continue with our discussion. We'll confirm the value. So anyway, if U is there, the Coriolis force is basically acting in the north-south or meridional direction. Now, suppose the wind is actually in the northern hemisphere. So northern hemisphere means latitude will be positive or F will be positive. If F is positive, then F Coriolis is minus Fu will be negative, right? Negative in the sense, the motion will be, it is minus j, right? So positive j basically represents south to north. So minus j in the sense that it will be like north to south. So what will happen? The wind will be blowing in the west-east direction, whereas the surface current, because once the Coriolis force starts acting, west to east we have the wind, the surface current starts to flow, and the Coriolis force starts acting. Because of this, there will be the Coriolis force will basically push the surface current towards the south. It is acting in the north to south direction. Since the F Coriolis is negative, this is minus Fu, and it is negative. Now consider that this is actually happening. This is in the northern hemisphere. Now suppose this is happening in the southern hemisphere. If it is in the southern hemisphere, then F will be negative, which means F Coriolis will be positive. We have Fu, which is a positive value. So the wind is west to east, it is blowing. The direction will be from south to north. So if a westerly wind blowing in the northern hemisphere will create a surface current which is 45-degree from the direction of the wind, which is displaced 45-degree towards this is basically towards the right of the wind direction. Whereas if the wind is blowing in the southern hemisphere, the surface current will be formed or will be pushed 45-degree to the left of the wind direction, right? So that is what is happening. Now this is in case of the surface current. Now as I said, this momentum is actually being transferred to the deeper layers as well. And if you look at as it gets uh, transferred, it basically creates a spiral-like structure. So here you can see if the wind is blowing like this, the surface current is actually moved 45-degree to the right of the wind direction. So this is showing in case of the northern hemisphere. And all the consecutive layers are creating a particular angle with respect to the surface current. And it is actually creating a spiraling kind of structure, like to as we go deep into the ocean. And at a particular point, the net motion will be almost zero. So, in the question, it is asking that what will be the net effect of Ekman transport. Okay, it is telling the net effect of Ekman transport is that water is transported at a direction 45-degree to the right of the wind direction, the northern hemisphere. Is it true or false? That is the question. What do you, huh? Yeah. Mm-hmm. Angle is increasing. Yeah. So it is creating a 45, it is moving more towards that direction actually. So, yeah. So if this is, so this will be 45-degree. So the next layer is actually driven by, or it is basically transported, or it is basically, what do you say, triggered by this surface current. So it will be having this, with respect to this current only, it will again create an angle. Then the next layer will create an angle with respect to this. So it will keep on increasing. So that's why we have this spiral kind of structure. So with respect to the just immediate layer, it is creating that angle. Yeah. So if you look at like if you take all the layers, the net transport will be like almost 90-degree. If you are talking about the surface current, then this statement is true. The surface current will make an angle 45-degree to the right of the wind direction in the northern hemisphere. But when we are talking about the net effect of Ekman transport, if we consider all the layers, it will be like 90-degree. Net transport will be at an 90-degree to the right in the northern hemisphere and 90-degree to the left in the southern hemisphere. So this statement is false. Yeah. So that is basically Ekman transport. Now the next question. The net volumetric, sorry, the unit sphere drop is used to measure what? What does it the unit sphere drop gives you? Selen, huh? Sorry? Yeah, yeah. So it basically gives you the volumetric transport by surface current. So generally in Ekman transport, say like this much volumetric transport or yeah, or like through surface current, this much volumetric transport, this much volume of water is actually being transported. So one sweat drop is basically 10 raised to 6 meter cube per second. With respect to, so this many meter cube or this many volume of water is being transported per second. That's what it basically means. Now the next question. Yeah. La Nina is a weakening of the neutral ENSO state with weaker trade winds and reduced upwelling in the eastern equatorial Pacific. True or false? So, what is El Nino and La Nina? What is uh, ENSO and all these things? You should know. Yeah. So, over the equatorial Pacific Ocean, we basically have strong equatorial Pacific. Over the equatorial Pacific, we generally have strong easterly winds, which is blowing from east to west. So we have like kind of like this. So, because of this easterly wind, surface water also move from the east to west along the equatorial region. So, the surface current flow from East Pacific to West Pacific. So, East Pacific is basically over this American regions. We have like America over here. I'm not like drawing perfectly, but just so you know. And over the Western Pacific, we have Indonesia and we have Australia over here. So this is a normal structure. We have easterly trade winds, which is blowing along the equatorial Pacific Ocean, which basically moves the surface water from east to west along the equatorial region. So the surface current flows from the eastern Pacific, from the eastern coast of America to the western Pacific to the Indonesian and Australian coast. So once it reaches Indonesia and eastern Australia, water sinks down and downwelling over the Indian Ocean. And so this water is actually coming from east to west. So it will accumulate over here and it will go down. Just downwelling will happen over the Indian Ocean and East Australian coast. And warm water in the Western Pacific increases temperature and evaporation, and wet, humid conditions prevail over the Western Pacific region. So over this region, due to higher temperature and yeah, so yeah, so you are telling it should be like it should receive equal amount of west side, it should have equal amount of solar insolation. Yeah, so if you look at the yeah, so in the Pacific generally, the Western Pacific Ocean is like warmer than the eastern side. One thing is because like the trade winds basically push the so even though it is uniform along the whole equator, because of the trade winds, it pushed the warm surface water westward. So what is happening is that as the wind blows from east to west, it is taking the water from the surface, right? So surface is basically having the warmer water. So we have so assume that it was the whole thing was having same temperature initially. Now, once the trade wind starts blowing, what happens is that it takes the warmer surface waters from the eastern Pacific to the western Pacific. So, if there is a deficit of water over this region, what will happen is that deeper waters will start coming up. So, upwelling will happen here. So, when upwelling happens, the deep cold waters is actually reaching the surface, whereas the warm surface waters is carried away to the western part of the ocean. Yeah. So because of that, the Pacific is warmer compared to that of the Eastern Pacific. So what happens is that so a low pressure system here the warmer waters is having a low pressure system. So because of this low pressure, a convective cell starts to. So this is what is happening in the ocean. We have like there is a east to west movement of surface waters. There is downwelling that is happening over the Western Pacific, and there is an upwelling that is happening over the Eastern Pacific. And here we have a low pressure condition, and here we have a high pressure condition. Now, because of this low pressure system, an atmospheric cell starts to develop, which has the convective currents, or like what do you say, the upward motion in the Eastern Pacific, and in the upper atmosphere, we have west to east moving air, and it will come and it will sink down in the high pressure region formed over the eastern Pacific. So, in the surface, we have surface moving east to west currents, which is taking the warm surface waters towards the western Pacific. And due to the low pressure system that is being formed over the western Pacific, a convective cell starts to form, which is having the convection over the eastern Pacific, and it travels eastward, um, cools and eventually sinks over the eastern Pacific. The cycle completes when the air becomes easterly trade winds. Again, it will have this east-west motion near to the surface. So this particular cell is known as the Walker circulation. So this is the Walker circulation. So just to the things you have to remember is first one, the Western Pacific is warmer than the Eastern Pacific. We have easterly trade winds blowing over easterly trade winds over the Pacific Ocean. Yeah, uh, easterly trade winds over the Pacific. Yeah, surface easterly trade winds over the Pacific Ocean, and there is downwelling that is happening over the Indonesian and Australian coast. And there is upwelling over the American coast. Yeah, this, yeah, kind of. Uh, not that I'm not sure if there is a connection for this in the ocean as well, like we talk about in the atmosphere. Because I think when you go like deep in the ocean, it becomes almost uniform. This happens only near to the surface. As you go deeper in the ocean, it kind of becomes uniform. The temperature and salinity becomes like almost uniform. As the water sinks down, the temperature will reduce and it will become uniform, I guess. So it doesn't have a connection in the deeper ocean layers. Mm-hmm. Okay. That I am not sure if I haven't read of anything like that. But I'm not sure if something kind of like that exists. Like, okay, yeah. So so basically, yeah, downwelling, yeah, and basically a high pressure region is there over the Eastern Pacific, and the low pressure region is found over the Western Pacific. And in the atmosphere, we have what is known as the Walker circulation. We have what is known as the Walker circulation, which basically has convection or upward motion in the Western Pacific and sinking motion in the Eastern uh, Pacific. So, can you say which region will be actually receiving more rainfall? Like which coast will be receiving more rainfall? Eastern coast. Eastern coast of why? If there is a sinking motion, it mostly shows clear sky conditions. If, like it is very difficult for clouds to form when a strong sinking motion is actually present near the surface. So the upward motion generally indicate the formation of clouds and rainfall. So you can't like say that it won't rain. I agree that like so it will rain also, right? It is not like the clouds will form, it will be carried to the Eastern Pacific and then it will rain there only. So once the cloud will form, it will rain in the Western Pacific, then the dry air will be reaching the Eastern Pacific. Yeah. So like generally where there is strong convection, that region will be associated with more rainfall. So that is the general idea. Wherever there is sinking motion, it will be mostly associated with clear sky conditions. It is very difficult for clouds to form. And the clouds doesn't sustain the rainfall for a long time. Once it is formed, it will rain out as well if enough moisture is available. So whatever clouds are forming in the Western Pacific will rain out there itself. From this, we can say that the Western Pacific, the coast of Australia and Indonesia will be receiving more rainfall. Uh, more rainfall. Okay. So now, yeah. So I said that the Western Pacific is actually having a high pressure, and the Eastern Pacific is actually having a low pressure system. Now, there is something called the Southern Oscillation Index. Uh, yeah. Oh, okay. No, no. We have low pressure over the Western Pacific only. Did I write it wrong? No, right? Western Pacific is associated with low pressure region. Yeah. The Western Pacific is associated with low pressure, so we have rainfall over there. Yeah. Yeah, Eastern Pacific has high pressure. I think I drew everything. It is looking so congested. Yeah, okay. Thank you. So there is something known as the Southern Oscillation Index, which is basically which basically gives you the pressure difference between Western and Eastern Pacific, West and East Pacific. So if the difference is the pressure difference is negative, Southern Oscillation Index is zero, then it is generally a neutral condition. And if it is positive, then we have uh, intensification of Walker circulation, which is known as La Nina. And if the Southern Oscillation Index is negative, we have what is known as El Nino. El Nino basically is associated with weakening of Walker circulation. And La Nina is associated with strengthening of Walker circulation. So here the question was, La Nina is a neutral ENSO state with weaker trade winds and reduced upwelling in the eastern equatorial Pacific. La Nina is a weakening of the neutral ENSO state. Is that correct? False. And weaker trade winds. That is also wrong. During La Nina, we have very strong trade winds. Strong east-west trade winds are present during La Nina condition and reduced upwelling in the eastern equatorial Pacific. We have very strong upwelling in the eastern equatorial Pacific due to strong easterly winds that is blowing along the equatorial Pacific. So the answer is false. So this basically shows the warmer Pacific Ocean and the convex. So here you can see the cloud is formed here and it precipitates out here, and this is the convective circulation. It has convection over the Western Pacific. It has strong westerlies in the upper atmosphere, and it sinks down in the Eastern Pacific. So this is the Walker circulation. This is in case of normal, and this is in case of La Nina. I hope it is clear. What is La Nina is basically clear. So during El Nino, so this is basically La Nina. During El Nino, what happens is that the trade winds weaken. So the east to west trade winds weaken. So what happens is that the water is not, or this transport of this warm pool, which we see in case of La Nina, which is mostly confined to the Western Pacific, it kinds of get extended towards the Central Pacific as well. As we already said, the trade winds are actually carrying the warm surface current from the Eastern Pacific, and it is carrying it to the Western Pacific, and it is basically accumulating it over there. So what happens is the trade winds weaken. Of the trade winds weaken, the western warm pool, which is mostly confined to the Western Pacific, will start moving towards the Central and Eastern Pacific. So we have warm pool over the Western Pacific, and Eastern Pacific is generally cooler. That's what we just saw. When there are strong west to east trade winds, sorry, east to west trade winds, right? So yeah, for normal and La Nina. So normal basically intensifies during La Nina. Now during El Nino, what happens is that this trade winds weaken. It becomes weaker. This east to west trade winds weakens, and this warm pool, which we earlier saw over the Western Pacific, will start expanding, and it will be seen over the Western and Central Pacific regions. So that contrast will not be that much. And what happens is that this convective cell that we had, this convective motion in the Western Pacific and sinking motion in the Eastern Pacific, will also shift. So we will have the convection mostly in the Central and Western Pacific. It will become weaker. The Walker circulation also weakens. So this is what happens during El Nino. Weaker trade winds, less rainfall will happen there. And this region will receive more rainfall compared to the other periods, like La Nina period. Eastern Pacific coast, like American coast, will be Californian and Peru. Yeah, they will be receiving more rainfall comparatively. So weaker trade winds, the western warm pool shifts to the central and eastern. Western warm pool extends to central and eastern Pacific. So that is basically El Nino. Now, the next question. Which of the major components of seawater have a concentration of 0.39 gram per kilogram or higher? So the seawater basically contains a large number of, sorry, yeah, except ion, all three are correct. So salinity is basically, so seawater basically contains a number of grams of dissolved salt that is present per kilogram of seawater. So it has a lot of dissolved salt. In that, chlorine tops the list, as you can see. The highest salt is basically chlorine. Then we have sodium. Yeah, sodium chloride and dissolved uh, ions. Yeah, I think it will be in the ionic state, I guess. Mm. Sodium chloride. Then I think it becomes soluble, no? No, it isn't water, I think so. Once it's become soluble, it will yeah, it will be separated. It will be yeah, it will be in the ionic state, I guess. The salt form means it will be like in the ionic state. Yeah, it will be present as Na plus and Cl minus once it is dissolved. So here the answer is except ion, all other are actually having. concentration greater than 0.39 gram per kilogram. Now, the next question is salinity-induced density differences are major drivers of oceanic circulations, especially in which regions or conditions. Salinity-induced density differences are major drivers of oceanic circulation, especially in which regions or conditions. So we know density change can occur due to temperature. It can happen due to salinity difference, or it can also happen with respect to depth. We already saw that. So the question is, salinity-induced density difference are actually driving oceanic circulation. This happens in which conditions or which region? In deep oceans and at high latitudes where temperature changes are small. Yeah, it is actually, yeah, it is, it happens in the deep ocean and at high latitudes where the temperature changes are small. It is correct. So in the surface mixed layer, it can't happen because it has like constant density. And in subtropical latitudes, it is mostly due to the salinity difference, I guess, rather than the density difference. So yeah, deep oceans and at high latitudes where the temperature changes are small are the correct answer. Now the next question. Surface salinity in subtropical latitudes is less. So subtropical latitudes have less salinity as precipitation exceeds evaporation. Is it true or false? The subtropical latitudes are actually having greater evaporation compared to that of the precipitation. So this statement is correct. So less salinity can happen when the precipitation exceeds evaporation, but over the subtropical latitudes, the condition as the evaporation is actually greater than the precipitation, and the waters are highly saline. So this is false, right? Yeah, because the yeah. So when you just logically think that because of since precipitation exceeds evaporation, then surface salinity is less. That makes sense. But in the subtropical latitudes, actually the condition is the other way around. The evaporation is actually higher than the precipitation, so it is highly saline. So that's why it is false. Now, which of the following are true? The equatorial Kelvin wave occurs during El Nino conditions. It occurs between Australia and South America. It is the moment of cool pool of water, tends to cause precipitation in the coasts of California and Peru. So, equatorial, yeah. So basically, over the western and eastern Pacific, if you look, the what you say, the sea surface height is also different. So the Eastern Pacific is actually at a higher height compared to that of the Western Pacific. So that also actually helps in that flow. Like water, the warm water actually flows from this to this region. This height also helps. So this is actually a bit higher compared to this. This is actually lower. So basically, it is very easy for the water to flow from this region to this region, from the east to the west Pacific. So during El Nino, what happens is that uh, this flow reversal happens between west to east. So when warm water piles up in high sea levels of Western Pacific, yeah. So here, when this water kinds of piles up due to, suppose during La Nina condition, here this warm water kinds of piles up. So this sea, then the sea surface height difference will be almost same. It will be like nullified. We no longer will have the sea surface height difference. So what happens is that this water will start flowing back to the Eastern Pacific. Once it gets accumulated over the Western Pacific, it begins to flow back towards the Eastern Pacific. This flow reversal happens from west to east, and it almost takes 4 months for the warm pool of the water to travel um, to this coast of America. From west to east, for it to flow back, it will take almost 4 months. And this is basic. This flow back is basically known as the equatorial Kelvin wave. So that flow back from west to east is basically known as the equatorial Kelvin wave. Yeah. And this warm water, so as it reaches the American coast, it basically warm waters is coming towards the American coast, right? So it will basically bring high sea surface temperature and precipitation along the Californian and Peru coast. This we already discussed during El Nino, since the warm pole is actually kind of shifting to the central and eastern Pacific. More precipitation will be seen over the Californian and Peru coast. So which of the following is true? The first one is that the equatorial Kelvin wave occurs during El Nino condition. Is it true or false? Uh, No, so this is East Pacific, this is West Pacific, right? So generally, the East Pacific, so it is kind of like this. Okay. So the East Pacific is higher and West Pacific is lower. This is the general condition. So during La Nina, what happens is that water will flow from the East Pacific to West Pacific, right? It will flow and the water will get accumulated over here, right? And after some time, yeah, so we don't have this sea surface height difference after some time. Now we have equal height. So what happens is that the water will start to flow back from the Western Pacific to Eastern Pacific. This is when El Nino happens. This reversal is when El Nino happens. And this reversal of flow from west to east is basically known as the equatorial Kelvin wave. Yeah, yes. So this is true. And it occurs between Australia and South America. Is it true or false? What we here, yeah, this is true. So here we have Australia and Indonesia in the Western Pacific, and in the Eastern Pacific we have South America. So that is also, yeah, it is a moment of cool pool of water. This is false. What is actually happening? The moment of warm pool is actually happening. And it tends to cause precipitation in the coast of California and Peru. Is this true or false? True. So California and Peru are American coasts, actually, Eastern American coasts. So yeah, it will create precipitation or it will cause precipitation in the eastern coasts of California and Peru. So except the third, all other three are correct. Now, strengthening of the water circulation leads to El Nino event. True or false? False. Mm, no. Which of the following are characteristic features of large subtropical ocean gyres? Uh, so what does it mean by ocean gyres are this circulation which basically carries. So we know that there are we know this global wind circulation pattern, right? We have this near to the equator, we have this east to west blowing trade winds. Then if we go on top, then the wind is actually in the opposite direction. So as we go along the latitude, we have this particular wind direction. So we know that these winds are trying to push the surface water or the surface ocean waters, and due to Coriolis force, it basically has a flow which is 90 degrees to that of the wind direction. So due to this, along the coastal regions or along the coast, we have a lot of oceanic currents that is actually flowing. So in the subtropical oceans, it basically forms a circular kind of structure due to this net transport of this because of the combined effect of the wind direction, wind velocity, and that of the Coriolis force. It kind of flows in kind. It kind of forms a kind of circle in the subtropical regions. So those circles or circulations are basically known as subtropical ocean gyres. So these are in the in the northern hemisphere, these subtropical ocean gyres are actually having a clockwise kind of circulation, whereas in the southern hemisphere, it is actually having a anti-clockwise kind of circulation. And along the, sorry, yeah, so generally, so the blue lines basically shows warm ocean currents, which basically carries warm water from the equator to the polar regions, and the blue regions are basically cold ocean currents, which is generally carrying cold water from the polar regions towards the equator. So this transfer of water from the equator to the higher latitudes generally happens along the eastern coast of the continents. So eastern boundary currents or the currents that are actually flowing along the eastern coast of the continents will be warm ocean currents, whereas the currents that are flowing along the western coast of the continents will be cold ocean currents. So the eastern coastal currents are generally warmer and western coastal currents are generally cold with respect to the continent I'm telling. So if you see along the along the eastern coast of North and South America, we have like warm currents like the Gulf Stream, North Equatorial Current, etc. And along the eastern coast of America, we have the warm North Equatorial Current and Gulf Stream, whereas along the western coast of the this is Africa, right? Along the western coast of Africa, we have this Canary Current, which is a cold current. So eastern coastal currents are generally warm, and the western coastal currents are generally cold. So here the question is, which of the following are characteristic features of large subtropical ocean gyres? They are driven by cyclonic wind circulation. Is that correct? Cyclonic, that is false because winds are basically like blowing in a linear form. It is from east to west or something. In the tropics, it is from east to west. So it is not due to a cyclonic. The wind circulation are like linear only. Next, you're able to hear me, right? Okay. The next one is they cause near surface waters to generally move in a clockwise pattern in the northern hemisphere. Is that correct? Northern hemisphere, it is clockwise. It is true. They cause near surface water to move in clockwise. So this is true. They cause near surface water to gently move in a clockwise pattern in the southern hemisphere. Is that true? It is false. It is anti-clockwise. Yeah. And they lead to warm water moving towards high latitudes along western ocean basin edges. So we can like classify it based on ocean, western ocean and eastern ocean. Also eastern coast and western coast. So I told you the western eastern coastal currents are warm and western coastal currents are cold. Now, when you look at with respect to the ocean, if you see, this are actually western ocean basin edge, right? If you look at in terms of the ocean, if you look, this is the western side of the ocean and this is the eastern side of the ocean. So when you are telling in terms of the ocean basin edges, the western ocean basin edges carry warm water, whereas the eastern ocean basin edges carry cold water. So this is true or false? True. So, and if this was in terms of continents, if you say it is like western coastal currents carry cold water and eastern coastal currents carry warm water. Now, the next question, the upwelling of deep sea water and downwelling of surface water occurs at what latitude? So, what does it mean by the upwelling of deep sea water and downwelling of surface water? So, basically, there is something known as the thermohaline circulation. The thermohaline circulation is defined as a part of the. So this is basically surface ocean currents. This movement are actually happening in the along the surface of the ocean. So what is thermohaline circulation? Thermohaline circulation actually happens that is driven by water density variation caused by. So this is basically driven by water density. So it is like lower denser water will sink, will rise and denser water will sink like we talk about in the atmosphere this happens with respect to depth, not along latitude like in case of the surface current. This happens with respect to depth. So this generally is driven by the water density variations caused by temperature and salinity difference. This is driven by water density variations due to temperature and salinity differences. Now, these circulations generally cannot be detected directly because this is very slow. We can't generally visualize, or we generally can't see these circulation. So these are generally inferred from the oceanic concentrations. So surface waters generally have very high ocean content because of mixing and photosynthesis, whereas deep waters generally have very less ocean because as we go deep, the aquatic organisms are increasing. So the oxygen intake is more. A lot of oxygen deficit will be seen towards the as we go deep into the ocean. So, uh, so this basically shows the ocean uh, like concentration of oxygen along the latitude over the Atlantic Ocean. So generally, the surface values are characterized by high oxygen concentration levels, and deeper levels are characterized by low oxygen concentration levels. So here we can see the blue lines basically show high concentration of oxygen, and the red lines show low concentration of oxygen. Sorry, it's the other way. Yeah. Yeah. Blue shows high and red shows low values. So can you tell me like which latitude is actually having this from the ocean concentration of ocean? Can you tell me like which is actually having this thermohaline circulation? Like over which latitude is actually this is happening? Like thermohaline circulation is happening. So this generally happens in the what do you say in the high latitude regions because over the equatorial regions because of the warmer the surface waters are mostly warm or because of the solar insolation that is coming the surface waters are always very light or it is generally having very less density. So it is very difficult for those water parcels to sink to deeper layers. Because of that, the high latitudes where we generally have very low insulation, we generally see this thermohaline circulation. For the surface waters become more denser, it will sink and the deeper waters come to the surface of the ocean. So the thermohaline circulation is mostly seen over the high latitude regions, like mostly over 70 to 80-degree latitudes, I guess. This is the answer. 70 to 80-degree latitudes. Yeah. I think we are moving on to the week 9 questions. So I think the things are clear, like basic properties of the ocean, thermocline, and El Nino Southern, ENSO, then the thermohaline circulation. And yeah, I hope. Okay, one more question is there. The next question is the Walker circulation is observed at, so we know it is over the Pacific Ocean. So where it is actually seen? Is it at high latitudes? It is at tropics? Uh, where is Walker circulation seen? Pacific Ocean is correct. Pacific Ocean at the high latitudes or Pacific Ocean at the tropics? Yeah. So it is equatorial Pacific Ocean. Whenever I say it is equatorial Pacific Ocean. So Pacific Ocean at the tropics is the correct answer. Yeah. So now this is, I think, the question. So for the week 9 of your NPTEL class, it is mostly talking about radiative forcing, climate change, sensitivity, etc. So I thought we will begin with a basic introduction of what is uh, radiative forcing. We know that the so I'll just give a recap of what is basically radiative forcing. So the total incident radiation that is being absorbed is given by Es absorbed as 1 minus alpha into S0 by 4, where S0 is 1360, which is the solar constant, is 1360 watt per meter square. Alpha is 0.29. And how much will be this value? It will be 1 minus 0.29 into 1360 by 4. How much it is? Yeah, it is approximately 240 watt per meter square. So this is basically the incoming solar radiation, F incoming. Now, the after it reaches the surface of the Earth starts re-emitting. The black body emission temperature, which is sigma T e raised to 4, should be equal to ES absorption at equilibrium. Or this is the basic idea. Whatever be the incoming, it should be going as well. So the actual surface temperature of the Earth, surface temperature of the Earth is 288 Kelvin. So based on that, if you see what will be sigma Ts raised to 4, how much is the surface actually emitting? How much it will be? 320 is coming. Ts is 288 Kelvin 5.67 into 10 raised to minus 8 into 288 the whole raised to 4. I'm getting a value of 390. Am I doing something wrong? Oh, so it is 390 watt per meter square. So the incoming is 240 and what is being re-emitted from the earth is 390. So basically there is a difference in the incoming and outgoing. So E surface minus E absorption, ES absorption is 390 minus 240 is equal to 150 watt per meter square. So this 150 watt per meter square is basically being absorbed by the what you say the atmosphere. So out of this, two-third is contributed by water vapor and 1/4 by carbon dioxide. Out of the warming that we see, sorry, yeah, two-third is almost contributed by water vapor and almost 1/4 is contributed by carbon dioxide. So the equation shows that how does a given climate state respond to the perturbations of various absorbing gas concentration values and concentration of aerosols in the atmosphere is basically given by the radiative force. So basically the difference between the incoming and outgoing radiation is given by the radiative forcing. It is defined as the net decrease in upward irradiance at the tropopause due to change in some climate change driver, such as change in the concentration of gaseous absorber or aerosols. So radiative forcing is defined as the net decrease in the upward irradiance at the tropopause due to change in some climate change driver, such as like concentration of greenhouse gases, aerosols, or something. So, if the radiative forcing is greater than zero, it means the incoming solar radiation is greater than the outgoing solar radiation. So, basically, there is an accumulation of radiation in the climate system. So, this basically indicates warming. And if the radiative forcing is less than zero, it means the incoming radiation is less than the outgoing radiation. It basically indicates cooling. Yeah. So, for a, and if we are doing for a zero dimensional energy balance model, Here we are considering the climate system that we are talking about has the troposphere. It has the land surface, and third, it has the ocean mixed layer, which we are assuming is approximately 100 meters deep. So the so this system of which combines all these three different surfaces is known as is what we are considering as the climate system. The energy transfer into and out of the climate system are basically, so we are basically neglecting mass and heat transfers. We are only considering through radiation. So the energy transfer into and out of the climate system are due to net absorbed shortwave solar radiation, which is incoming, and what is outgoing is the net outgoing long wave thermal radiation. So C dt by dt is given by F incoming minus F outgoing. So this is the land surface. Then we have the ocean. And we have the troposphere. Suppose this is the tropopause. We have incoming solar shortwave radiation, and we have outgoing long wave thermal radiation. So F incoming is a shortwave irradiance being absorbed by the climate system, and F outgoing is a net outgoing long wave irradiance from the tropopause. C basically gives the heat capacity per unit horizontal area. Of the climate system. So if this much difference is there in the incoming and outgoing radiation, how much temperature change will happen with respect to time? That's what it basically shows. And C is the heat capacity. So heat capacity, we are considering the heat capacity of ocean because the heat capacity of atmosphere and land surface is very small compared to that of the heat capacity of yeah, compared to the heat capacity of the ocean, land and atmosphere is having low values of heat capacity. And since we have 70 percentage of the ocean, which is covered by 70 percentage of the earth covered by the ocean, C is basically 0.7 into heat capacity of heat capacity of ocean mixed layer into 0.7 is what we use as C. So in order to find out if this much difference is there in the incoming and outgoing radiation, how much temperature change it will create to the climate system, we have the equation C dt by dt is equal to F incoming minus F outgoing, where C is the specific heat capacity of the ocean mixed layer into 0.7. So we are considering the specific heat capacity of ocean because the specific heat capacity of land and atmosphere is very small compared to that of the water, and 70 percentage of the Earth is basically covered with ocean. So 0.7 into C of ocean mixed layer is what we consider as the value of C. It's basically a constant value. C is approximately 1 gigajoule per meter square Kelvin, or C is basically 1 gigajoule is basically 10 raised to 9 joule. So this is the value of C. 10 raised to 9 joule per meter square Kelvin. So we know that F incoming is basically ES absorbed is equal to, yeah, this, okay, like, um, I was just telling you what is the value of C. So this C is basically a constant. Only one C is there. The C is having a value of 10 raised to 9 joule. Okay. Yeah, into 0.7 will, yeah, 10 raised to 9 into 0.7 will come as. Yes. So into 0. Anyway, it will be like very less. So we can assume it to be 10 raised to 9. It's okay. If you divide, or sorry, multiply 10 raised to 9 into 0.7. Yeah, 7 into 10 raised to 8 to do. Yeah. Okay. Yeah. So F incoming is approximately ES absorbed is equal to S0 by 4 into 1 minus alpha is equal to 240 watt per meter square. So we know this is a constant value, whereas F outgoing depend on the temperature, the concentration of water vapor, carbon dioxide, etc. in the atmosphere. F incoming is a constant value, whereas F outgoing is dependent on the temperature and the concentration of greenhouse gases like carbon dioxide, water vapor, etc. So F incoming minus F outgoing is basically a function of the temperature and the chi is the concentration of the greenhouse gases. So it is basically a function of temperature and chi. So in a steady state climate, the temperature is constant, which is T is equal to TSS, and chi is equal to chi S, which is the concentration of greenhouse gases. And also, the change in temperature with respect to time will also be zero. So C into dt, SS by dt will be zero in a steady state climate. So if we slightly perturb the climate, that is, we increase the temperature from T to TSS plus T dash T, or chi to chi SS plus chi dash T. This is the new temperature and new concentration. We will get an equation C dt dash by dt is equal to dou F by dou T into T dash plus dou F by dou chi into chi dash. Once you differentiate, um, yeah, and then this is, mm, okay, I'll write it from the book. C dt by dt is basically F of T and chi, right? Ah, okay. df by dt, t dash, yeah, it is not common, you're telling. df by dt into t dash plus df by dk into chi dash. So I will just once check the final equation. Yeah, I was just checking the equation. So it is df by dt. The bracket is common only actually. It's df by dt into t dash plus. Okay, okay. Yeah, it is by Taylor series expansion. Okay, it's not a bracket. It's like df by dt into t dash plus df by dk into chi dash I guess. Yeah, after doing the Taylor series expansion, it is coming like this. So the f will be basically a function of c dt dash by dt will be f of t s s by t dash comma chi s s plus chi dash of t. After doing the Taylor series expansion, getting this formula df by dt into t dash plus df by dk into chi. dt by dt, right? This is dt by dt. Okay, okay, okay. Okay. Okay, that dt is t prime and dx is chi prime. Okay. Okay. Yeah. And then a climate feedback parameter is defined, which is given by dou f by dou t. A climate uh, feedback parameter is defined as minus df by dt. And once some perturbation is made, the feedback once we make some perturbation to the climate system, the feedback response time is given by tau is equal to C by alpha, which is approximately 10 raised to 9 seconds or approximately 30 years. Once we make some perturbation to the climate system, the time period up to which it takes for it to come to the steady state is given by approximately 30 years. And the climate sensitivity S is basically given by the radiative forcing by alpha, the feedback parameter. Yeah, climatology value. Yeah. Mm. So in order to account for these slight variations. That's just actually okay. I think we will solve two problems and then we will stop for today. So the question is the initial radiative forcing uh, from a carbon dioxide increase is 3.71 watt per meter square. Initial radiative forcing from a carbon dioxide increase is given by 3.71 watt per meter square. If the total climate feedback parameter from all the feedbacks is 1.92 watt per meter square Kelvin, the equilibrium temperature change S is equal to question mark climate sensitivity for this forcing. So the climate sensitivity is basically given by radiative forcing divided by the feedback parameter alpha. So in this case, the radiative forcing is 3.7 divided by alpha is 1.92. How much it will be? Yeah, it is approximately 1.93 Kelvin, right? The unit will be Kelvin, no? The second question, yeah, the second question. The climate system has a heat capacity of, so C is given. C is 4 into 10 raised to 9 joule per meter square Kelvin and a relaxation time tau of 20 years, which is basically 20 into 3.15 into 10 raised to 7. So what we need to find? We need to find alpha, the climate feedback parameter. So tau is defined as C by alpha, which means alpha is equal to C by tau, which is equal to 4 into 10 raised to 9 divided by 20 into 3.15 into 10 raised to 7. How much it will be? Yeah, will be approximately 6.35 watt per meter square Kelvin. Yeah, that is alpha. Now, the third question. The water vapor feedback is considered a positive feedback because, yeah. So, water vapor feedback in the sense, we know that there is a increasing greenhouse gas concentration in the atmosphere. Because of the increased greenhouse gas concentration, what happens? There is what is known as a global warming. So, if there is an increase in temperature, what will happen to the water vapor content in the atmosphere? Warmer water will be able to hold more, or you remember we learned about saturation vapor pressure and all these things.
So, if an air parcel is warm, then there is more space between the molecules. Whereas when the water vapor is
When the what you say, when the temperature or the parcel is cool, it has less space between the molecules. So which one will be holding more water vapor, warm parcel or cold parcel? Cold air parcel. Yeah. Yeah, so warm air parcel will be able to hold more water vapor. So if we means that the atmospheric temperature is increasing, what it basically means, the water holding capacity of the atmosphere is also increasing. So what happens? There is increase in greenhouse gases, then there is global warming, which is basically increasing the temperature of the atmosphere. So increased temperature also means more evaporation. So there will be more evaporation, and the atmosphere
Capable of holding more amount of what do you say, more amount of water vapor. So once the water vapor is also a greenhouse gas, right? So if there is more amount of water vapor in the atmosphere, again it will lead to global warming. So it basically is acting as kind of a feedback loop, a positive feedback loop.
Positive feedback.
Yeah,
Yes.
positive feedback loop. So that is what is basically, so each thing is actually driving to the, it is enhancing all the effects. So among this, which one is yeah, why water vapor feedback is considered as a positive feedback loop? That is the question. The first one is increased temperature leads to more water vapor in the atmosphere. Is it true or false? Does it apply?
True.
Yes, it is true. Second one is water vapor is a greenhouse gas.
True.
True. Increased water vapor leads to decrease in outgoing long wave radiation. Is it true?
True.
Increased water vapor lead to decrease in, yeah. And the third one, increased temperature leads to less water vapor cooling the planet. Is it true?
False.
False. So these three applies actually. Now the last question. A negative radiative forcing means that we have a mean cooling effect. Is it true or false? Negative radiative forcing. If RF is negative, it means warming or cooling. So radiative forcing is basically F incoming minus F outgoing. If RF is negative, what it means? It means like more radiation is incoming than it is outgoing. So it means warming or cooling. F incoming is
Warming.
Yeah, it basically means warming. So it is true or false?
False.
Just a second.
False.
I think yeah, just a second. Yeah, so it is false. Yeah, I think we will stop it here today.
Yes, ma'am.
Yeah.
Stop.
Okay then. Thank you.
Thank you, ma'am.
Yeah. Bye.